Welcome back to this NPTEL course on principles of polymer synthesis. In the last class, we started talking about the design principle of chemical reactors, and we ended the class by talking about the general very simplified design equations of three of the reactors: batch reactor, and then two kinds of flow reactors. One is continuous start tank reactor and another is plugged flow reactor. So, we will continue in the same vein today. So, the topic of today is the continuation of the design of chemical reactors, the principles. So, we have talked about the design principle of CSTR, the plugged flow reactor, the batch reactor. Today, we are going to start talking about the design principle of packed bed reactor. We did not introduce this at all when we classified the reactors before, but now I am going to tell you that this is also a kind of flow reactor other than your CSTR and PFR. So, packed bed reactor, this is PBR. So, basically you have a cylindrical shell which is vertically oriented. So, you have a vertically oriented shell and you have a shell like this, and your flow is often driven by gravity, and this is called a packed bed because there is a fixed bed of catalyst inside. There is a fixed bed of catalyst inside. So, the reaction occurs, the catalyst will catalyze the reaction and the fixed bed of catalyst is there. So, that is why the name packed bed. So, obviously, then this is a heterogeneous reaction, unlike your homogeneous reaction. For example, in CSTR, if you have a liquid homogeneous reaction that you are doing, you generally use CSTR, continuously start tank reactor. If you have a gas that you are gas reaction, if you are having a gas that you are doing a reaction, say you are using ethylene, you are making a polymerization polyethylene, then you can use a plugged flow reactor. Typically for gases you will use that flow that kind of flow reactor, and for liquids you will use CSTR, homogeneous. Now, for PBR, packed bed reactor, it is a heterogeneous reaction. Now, reactants enter from the top and they will flow through the catalyst bed, and of course, then there will be a concentration gradient and the reaction will occur on the catalyst, on the surface of the catalyst pellets. So, reaction occurs on the surface of catalyst pellets, and the reaction rate, you have seen the reaction rate is a function of volume for plugged flow reactor. Allow me to show you the previous page here. So, reaction rate is a function of volume in the plugged flow reactor. Here the reaction rate basically is not a function of volume of the reactor, but it is a function of the mass of the solid catalyst, So, if you are looking at the mole balance equation, it was dFj dV equals to Rj for the plugged flow reactor, where your R, the unit of R was moles per second meter cube. So, that was the unit, because this is rate of generation per unit time per unit volume. If you remember, your Gj was equals to Rj into V, so on and so forth. So, now for catalytic reaction, because this is a catalytic reaction, you are defining another rate of generation, where you are using basically the unit as moles per second per kg of catalyst. Okay. Instead of meter cube, you have a kg there, or the weight there. So, ultimately instead of this, your design equation will become dFj dW equals to Rj prime, just to differentiate this Rj with that. In general, when you are writing design equation, you can just write Rj, but overall then this W is the weight of the catalyst, and that is why it depends not on the volume. Reaction rate actually depends on the weight of the catalyst. So, to summarize up to this part, what we have is this thing. So, you have the kind of reactor which is a batch reactor, you have say CSTR, you have plugged flow reactor and you have packed bed reactor. So, if you are doing the mole balance for batch reactor is dNj dt equals to Rjv uniformly start, let us say. CSTR is V equals to Fj0 minus Fj divided by minus Rj. Okay. PFR is dFj dV equals to Rj and PBR is dFj dW equals to Rj dot. Okay. Now, one thing you have to keep in mind, in actuality when we are doing the reactions, you have to look at the conversion. Here all these design equations, they do not contain the term conversion. You want a particular conversion, then you want a particular volume. Let us say if you are looking at CSTR, CSTR is V equals to flow rate in minus flow rate out divided by rate. Here we do not have the information of conversion in this particular form. So, ultimately then you have to mold your design equation in such a way that it will contain that information of conversion. Now, again we will veer a little bit away from chemical reactors at the moment. So, what is conversion? So, when we talk about conversion, suppose a molecule A is reacting with another molecule B, two different reactants, and then it is producing say C plus D. On the basis of which component you are going to calculate the conversion? That is a question, whether on the basis of component A or on the basis of component B. So, to start with, we will try to have a look at that particular question. So, let us say you are talking about this reaction, and as I told you, it may at times appear as it is not a class of polymer at all, it is a class of simple chemical reactions and physical chemistry, but it is not true. Things are actually interrelated and we are talking about the basic principles laying the foundation of the design of chemical reactor, and for that we have to start from the most basic level, and that is what I am doing, just to make things much more easily understandable for you. So, just bear with me. So, this is the reaction, let us say you are considering this particular reaction. So, A equals B by A, B, C by A, C, D by A, T. So, if you are, so the conversion based on A as the basis is equals to moles of A reacted divided by moles of A fed. So, for a batch, so if you are defining the conversion on the basis of A, then it is this. What is the moles of A fed? So, for a batch system, this moles of A fed is basically equal to the amount of A at time 0. To start with, whatever amount of A is there, that is the moles of A fed for batch system. For flow system, for example, CSTR or PFR or PBR, this moles of A fed is basically equal to the amount of A entering the reactor. So, this difference you have to keep in mind. So, flowing, so amount of A that is coming into the reactor, that is the moles of A fed, but as such you are not feeding anything into the batch reactor, everything is inside when you are starting the reaction. So, basically that is the moles of A at time 0, t equals to 0, that is the denominator then. So, let us say you are talking about this particular reaction A plus 2B equals to 2C. So, for this the conversion you will define on the basis of A or on the basis of B. Let us say you define on the basis of A, then you start with 1 mole of A and 1 mole of B. Okay. So, now when half a mole of A has reacted, then you have half mole of A, and since 1 mole reacts with 2 moles, so basically half a mole actually already has reacted with 1 mole of B. So, you basically now have 0 mole of B. So, what is the conversion at this point? Moles of A reacted, which is half, divided by total number of moles fed to start with, that is half. What happens when you go to 0 mole of A? So, another half mole has reacted. So, basically another 1 mole of B has to react. So, this becomes minus 1 mole of B, and your X A then will become, so moles of A reacted 1, moles of A starting is 1. So, this is 1. So, when you are talking about extent of conversion, you have to look at, you have to choose that particular reagent, that particular chemical as the basis for which you can go to 100% conversion, because 100% conversion is the physical reality. So, when you come into the equations, you have to choose that particular reactant as the basis for which your conversion could actually go to 100%. So, if you look at that, this taking the A as the basis does not work, because you cannot go to, you cannot actually formulate a situation where your conversion is 100%, because this is unrealistic situation. So, you have to take B as the basis. If you take B as the basis, again you start with 1 mole of A and 1 mole of B, then when it becomes half a mole of A, you already have 0 mole of B, and that actually tells you the conversion is full 1 mole has reacted divided by 1 mole you started with. So, this is 1. So, basically in this particular situation you have to take B as the basis to calculate conversion and not A, otherwise you will be wrong. And basically here your B is the limiting reagent, because B is in higher amount with respect to this, you need more amount of B. So, B is your limiting reagent. So, in whatever reaction you are tackling, when you are trying to find the conversion, now you know this particular question is important, because we are trying to put this conversion into the design equation, then only we start to gain an understanding how much conversion, for how much conversion, how much volume for example here is required. So, in order to then calculate the conversion, we have to find out what is the limiting reagent. With respect to that, in this case the B is the limiting, with respect to that you have to then define conversion. So, in this case for this particular reaction you define the conversion with respect to B and not with respect to A, otherwise it will be wrong. So, the next step then will be to express the other components. Now, we again go back to A, we will go back to this general expression, and let us assume that A is the limiting reagent, because we are not putting what is small b, what is small a, so on and so forth. So, if we have a conversion with respect to A, considering A is limiting reagent, which is not this example, this is a specific example, then we have an expression of X A that we are getting. Now, what we have to also do is that other components, components B, C, D, all of these components, the amount of those components you have to express in terms of that X A, that is the extent of conversion. All of those components you have to express in terms of X A. That becomes important when you are designing, when you are trying to find out if you are using a particular reaction for a particular reactor, then what kind of yield you can expect at what kind of time, say if you are talking about batch reactor, and what volume when you are talking about CSTR. So, things hopefully will become clear with time. So, now the next step is to express other components in terms of X A, that is the conversion with respect to A. So, in terms of X A we are trying to express this thing. So, let us say you are again taking this general reaction, this is your general reaction. Now, if you are looking at the moles of A at time t, that is equal to the moles of A at time 0, that is moles of A that is fed, minus this term, this is the moles of A that has been consumed. Similarly, you can also find out, so I am trying to find out the amount of all the other species in terms of the conversion which is X A, which will be extremely useful afterwards. This is N B 0 minus B by A into N A 0 X A. Same way your N C will be N C 0 plus C by A into N A 0 X A, and N D will be N D 0 plus D by A into N A 0 X A. Okay. So, this is something for a if you are looking at, for example, a batch reactor, or if you are looking at, for example, a CSTR, then these things will be useful after. So, from here then the total moles, whatever is the total moles of all the species at time t, total moles at time t is Nt equals to sum of j, all the species, Nj equals to total moles to start with, total moles fed plus d by a plus c by a minus b by a minus 1. So, these are all the coefficients here for the reaction into Na0 into Xa. So, this is the total moles at time t. So, this is the total moles of product formed, this into this, and this is the total moles of reactants consumed. Total moles of reactants consumed is B by A into Na0 Xa plus Na0 Xa consumed. So, this is the subtract. So, your stoichiometric coefficient of B is minus B by A, of A is 1, minus 1, of C is C by A, and the stoichiometric coefficient of D is D by A. So, these are nothing but stoichiometric coefficients. So, in general then your Nt will be equal to sum over Nj will be equal to Nt0 plus sum over J, means all the stoichiometric coefficients you add up into Na0 Xa. Now, what will be the batch reactor design equation in terms of conversion? So, if you are looking at this particular reaction, for this particular reaction, let us say the conversion is Xa. So, then in terms of conversion, what is the batch reactor design equation? So, let us say you are saying the conversion is in terms of A is the basis. So, you are defining the conversion in terms of A for this particular reaction, then your Na at any time whatever amount of species is there is Na0 minus Na0, this we already told, Na0 into Xa. Now, the batch reactor design equation is nothing but dNA dt equals to RAV. We already talked about that, rate of accumulation is equals to rate of the reaction, because nothing is going in, nothing is coming out. So, you might as well ask the question then, how long you want to leave the reactants in the batch reactor in order to get a certain amount of conversion. That is the question that is related to the same question in which you are trying to formulate your design equation with respect to the conversion. So, if you now differentiate this with t as a function of t, I mean with respect to t, that is the right word. So, dNA dt, so this is constant that goes, so that will be equal to minus Na0 into dxa dt. So, ultimately if you into dxa dt, so that will become so dNA dt is RAV. So, if you just replace that and if you integrate after, your t, the time will become Na0 0 to xa into dxa minus RAV. So, this is the design equation. So, if you want to have a conversion of Xa for this particular reaction and your rate of reaction is Ra, rate of reaction with respect to, say, if you are looking at A, the disappearance of A, if it is Ra, then, and this is the total volume of the reactant, then the time taken for this conversion is this. So, in terms of the design equation, so you know then why it is useful to formulate the design equation in terms of the conversion. Now, what happens in case of a flow system? This was a batch system. So, if you are looking at the flow system, this is in general true for all, say for example, CSTR or PBR or PFR. So, if you are looking at the flow system, then you can write down the equation the same way. Instead of Na equals to this, you can write down Fa equal to Fa0 minus Fa0 into Xa. So, molar, this is the molar flow rate of A leaving the reactor, molar flow rate, because moles per second, molar flow rate of A leaving the reactor. This is the molar flow rate of A fed into the reactor minus this into Xa, just analogous to this X. So, this is basically the molar rate of consumption of A. So, this becomes then equal to Fa equals to Fa0 into 1 minus Xa. So, in general then just the same way as we treated this thing. So, you can now see already that this is for the batch reaction, the particular treatment was for the batch reaction. For the flow reaction, this will be replaced by the flow. The same way, if you treat this, you will get the general relationship, which is total flow is this F T 0 plus sum over j nu j into F A 0 into x A. So, if you are writing the mole balance, then for CSTR, the mole balance for CSTR is nothing but F j 0 minus F j divided by minus R j, the general mole balance that we had derived, that is equal to F j 0 is nothing but F A 0 for the species A minus F A divided by minus R A. So, the V, so if you now replace F A with this particular expression, so if you replace that, so ultimately your V becomes equal to F A 0 into x A divided by minus R A. So, this is the ideal CSTR design equation, steady state situation in terms of your conversion. So, this volume is the CSTR volume required to achieve a conversion of x A. Again, to recall, CSTR is your flow reactor, one of the kinds of flow reactors, that is your continuously stirred tank reactor. So, this is the expression then. And what is the expression for PFR, plugged flow reactor, for example? Again, you can derive this for yourself. This is the general design equation for plugged flow reactor. If it is packed bed, it will be dFA dW. Now, if it is plugged flow, this is dFA dV. Okay. So, that is equal to Ra, and Fa again for all flow reactors in general, we have already shown you this thing. So, Fa is nothing but Fa 0 minus Fa 0 into x A. So, here ddV of Fa will give you minus Fa 0 into dxa dV. So, which is nothing but R A. So, and then if you integrate after, what you will get is that V equals to F A 0 integral 0 to x A dx A divided by minus R A. You cannot avoid this kind of calculations when you are designing chemical reactors. So, it is better that you are introduced now to it, if you are planning to take further courses on chemical reactors after in a more detailed way. So, this is important. So, this is the design equation of PFR in terms of the conversion. For PBR, you can derive for yourself. For PBR, that is the plug, that is the packed bed reactor, that will be W equals to F A 0, similar to this 0 to x A dx A divided by minus R A dot. Okay. So, that will be W, and here it is V, because the conversion depends on V volume for the plugged flow reactor, but conversion depends on the weight of the catalyst for the packed bed reactor. Okay. So, that is that. So, what we have done now is to derive the design equations until now, to derive the design equations in terms of the conversion, and we also gave you a concept of how to calculate the conversion. So, whatever reaction you are talking about, when you are looking at the conversion, you should look at the limiting reagent. With respect to that, you have to calculate the conversion, because if A is reacting with B, you can have two kinds of conversions that you can define. One is with respect to A, that is amount of A consumed divided by amount of A that you started with, if it is the batch reactor, or it is the amount of A consumed divided by amount of A fed in case of a flow reactor, or you could do the same for your reagent B. But in one of them, the calculation will be wrong, because one of them is basically the limiting reagent. So, if one of them is the limiting reagent, you will use that particular reagent as the basis of calculating the conversion, otherwise the calculation will be wrong. And then we showed you through simple calculations how the design equations will ultimately reduce to an equation. Your general design equations will ultimately reduce to equations in which you have the term of conversion. So, that with respect to conversion, you can correlate the volume of the reactor, or say volume of the reactor when you are talking about a, say for example, the flow reactor, say CSTR, your continuous start tank reactor, or volume of the reactor, say if you are talking about another kind of flow reactors, say plugged flow reactor. You can relate to weight of the catalyst when you are talking about packed bed reactor, or you can relate the conversion to the time when you are talking about batch reactor. Everything is inside. So, as a function of time your conversion will evolve, and as I told you, your conversion does not change as a function of time when you are, say for example, talking about CSTR. Whatever conversion you are getting, whatever species you have, say when you are talking about species A, if this A is basically a reactant that you are feeding, then there is a flow rate in for that reactant, and then there is a flow rate out, because all the A is not reacted, let us say, and then there is a particular conversion. This conversion does not change as a function of time. This conversion does not change in an ideal steady state CSTR as a function of space, that means everywhere the conversion will be the same. Now, if A is your product, so their starting stream does not contain A. So, in that case your starting stream, so F A 0, that means the molar flow in of A is 0. So, accordingly you put your mole balance. In general there will be some molar flow rate in and there will be some molar flow rate out. Okay. So, now let us see how this particular thing could be useful for us. So, what we have done here, so this equation is important. Let us start with say CSTR. So, your volume is related to conversion. So, for this kind of this amount of conversion you want this volume. So, let me ask the simple question, what is the volume of CSTR required to achieve this specific conversion of X A? So, let me write down this particular equation again. V equals to F A V equals to F A 0 into X A divided by minus R A. So, what is the volume of CSTR necessary in order to have a specific conversion of X A? So, what you will do in order to find that out? If you plot F A 0 by minus R A as a function of X A, say you will get this kind of plot as a function of x, let us say, or X A. So, I am just putting it as a X A dash. So, at a specific X A value of X A dash, what is the value of V? So, let us say on this particular curve, this is the point at which you have conversion of X A dash. Then if you are completing this particular rectangle here, if you let us say you complete this particular rectangle here, then what is the value of F A 0 minus R A at X A prime or X A dot? That value is this value. So, at this point the conversion is X A prime, and at this point the value of this plot, this thing, this value is this. So, here it is F A 0 by say minus R A prime. F A 0 is constant and your rate of the reaction may vary with conversion. So, let us say I am putting minus R A prime here. So, this F A 0 by minus R A, this will take a specific value of F A 0 by minus R A prime at a conversion of X A prime. So, this parallelogram, so ultimately this, not parallelogram, excuse me, wrong choice of word, this rectangle that you have, if you take the area of this rectangle, that will be this length into this length, this length into this length. So, that is this F A 0 into X A prime divided by minus R A prime in this case. So, at a particular conversion, if you are looking at a particular conversion, you plot. So, the idea then, to summarize from this here, the idea is if you plot F A 0 by minus R A versus X A conversion, this is called, this kind of plots are called Levenspiel plot. So, if you plot this, then the area of the rectangle with a base X A and with a height of Fa0 minus Ra will give you the volume of the CSTR necessary for that specific conversion XA. So, if you are targeting a conversion of XA prime, then you take the area of the rectangle with the base XA prime and the height Fa0 by minus Ra prime, because Fa0 by minus Ra prime is the value of Fa0 by minus Ra at a specific conversion of XA. Remember, Fa0 does not change, molar flow rate in does not change, however, the rate of the reaction of A, whatever, so the rate of generation of A or whatever destruction of A depends on whether it is a reactant or product, that may vary with conversion. So, that is why you have the graph that is going like this, it is not a horizontal line like this. So, it is changing. So, this ratio changes with conversion. So, you construct that rectangle and the area of that rectangle will give you the volume. Okay. Now, so finally, what I will do is, let us say before I complete this particular class, I will try to impress upon you this particular fact that, as I told you, this Ra, this varies, this can vary with conversion. So, in order to construct this particular plot, that means for every XA to get the corresponding value of this, or in other ways to know the nature of this function, how it is going up like that, or which way it is going up like this or it is going up like this, you need to have the rate of the reaction, you have to express that, you have to know the rate of the reaction in the functional form as a function of the conversion. Once you know that only, then you can, for all the values of XA, different values of XA, you will know this particular value, because Fa0 you know, and if you know the value of Ra, if you know the Ra as a function of XA, then you can plot this particular graph and you know this value. So, in the next class we will start with developing this concept little bit more, because the time is up for this class. So, we will keep talking about the chemical reactors then in general, and we start with this particular concept again. Till then, thank you and goodbye.